do is find the inverse matrix and I'm done. Right? But that seems at odds with what we did last time, doesn't it? Because we had these solution sets. Remember those annoying things with free parameters in them? So there wasn't just one solution, there was like a lot of them. How does that work then? Because this says that the solution, right, is A inverse times B. So I guess logically you could say, well, maybe there's more than one A inverse. Sorry about that. We can prove from algebra the inverse is unique. So that is a unique solution. So on the basis of our experience, we've discovered one of the theorems of linear algebra, which is that there's a unique solution if and only if the inverse matrix of the coefficient matrix exists. But if you've got multiple solutions, like we saw last time, that means that no inverse matrix exists. What's that, Isaac? All right, I'm coming. Just a second. Let me give them something to work on here. It's okay. I'll take them. So I want you guys to try to work this out. We've got A times B times C times D times another matrix, let's say E, F, G, H, right, equals to 1, 0, 0, 1. I want you to find E, F, G, and H as functions of A, B, C, D. You should assume that AD minus BC is not equal to 0. Exercise. You have 2 minutes. All right, Isaac. Got your wish. I'll leave the mic here. All right, anybody who not already know the answer, figure it out? Actually, anybody know the answer? No? Oh. I say we let E, F, GH equal to 1 over AD minus BC, DA minus B minus C. Let's try it out. Let's see here. So we get AD minus BC. We get minus AC plus AC. Well, let me say A minus CA plus AC. And then we get DB minus BD. And finally, minus BC plus AD. Also known as 1, 0, 0, 1. Woo-hoo. I cheated. Yes?
AD minus BC, what is that on in? Like, it starts with the year and
Ah, it has a name, yes. So what I'm showing you guys is the formula for the inverse of a 2 by 2 matrix, right? A, B, C, D. Inverse. I'm just kidding. It takes me at least a half hour to work this thing out. Even so, I think I have to cheat. I mean, I can show you. We can try to solve it a certain way. I can show you a way we could try. But yeah, that's a known formula. I tell calculus classes this because it's important. And yes, the determinant of A, B, C, D is that quantity which we need to be non-zero. Anyway, more on that later in the course, of course. All right, so sorry, I got distracted by inverse matrices. Getting back to the story about systems, no, there's not always an inverse matrix, so it's not always this easy. All right? But we can always write a system of equations as a matrix column equals to another vector problem, right? So what does it matter that you can do this? Like, who cares?
you can run that through MATLAB and do it a lot faster.
If you're what?
You can run that through MATLAB and do it a lot faster.
Well, yes, if we were just going to use MATLAB, then we should just hang up our, I mean, but the point of this is you know, sometimes you want to walk without rhythm as to not attract the worm, things like that, you know. So you got to know what's out there as to not, run into the things. You could use MATLAB, right? But if you use it without understanding, well, that's a dangerous thing as well, right? So that's one of the things we're hoping to get from this course is an understanding of what you're looking at in MATLAB, right? So, where was I? Sorry. Oh, yes. 3 minutes. Woohoo. All right, that's enough to make a point. How about this? Discussion. If we have AV, or let's say A, well, yeah. See, this is why I don't want to use X a lot of times, because I like to talk about multiple solutions, right? So what happens when you talk about two solutions if you use X here? Then you've got AX1 equals to B and AX2 equals to B, but what is X1 and X2? It's these guys. So then I run into that. So that's why I usually change letters and say something like AV1 equals to B1 and AV2. Let me put 0 here for a second. If you have two solutions to the homogeneous problem, right? Then check this out. What's A times V1 plus V2? So using this proposition, which I have proved none of. Sadness. I'll deal. Exactly, because this is AV1 plus AV2. In fact, I could even throw in what? I could throw in a C1 and a C2 here, just the same, right? And I would still just have C1 and C2 there, right? And I would just have C1 times 0 plus C2 times 0, which would, as you guys are telling me, be 0. So it is an absolute triviality to show that the sum of homogeneous solutions, in fact, a linear combination, this is a linear combination. Let me write it out in more detail. I'm saying C1V1 plus C2V2. This is a linear combination of V1 and V2. So a linear combination of homogeneous solutions is once more a a solution. If you think about that, that would be a much sort of harder thing to convince yourself of in the scalar notation, right? It's absolutely obvious here. What if you had, let's raise the stakes a little bit again. What if I have AV1 equal to B1, and if I have AV2 equal to B2, right? Then if you look at A times C1V1 plus C2V2, what do you get? By the products, by the matrix multiplication properties, we have this distributivity, but this is B1, right? And this is B2, and we get C1B1 plus C2B2. So it's not a solution this time, right? I mean, well, solution to what? So we have a solution with this, so like, this is like, say, force 1. This we could think of as force 2. And this right here would be linear combo of the forces, So the way to think about this, I mean, this is an example of what's called the principle of superposition. The response from B1 and the response from B2 from the system A, well, if you face a linear combination of the forces, then you just do the same linear combination of responses. In other words, the net outcome for the system is the sum of its parts. This is the superposition principle. Many physical systems satisfy this superposition principle, which underlies the fact that they're a linear system. Another thing you could do is, could you get a solution to the homogeneous problem? Check this out. So if you take, and if you look at A times, well, oh well, if I had these were both B, if I had B1 equals to B2 equals to B, right? Then if I had A of V1 minus V2, I would get AV1 minus AV2, right? Which would be B minus B, which would be 0. So if you have two solutions to an inhomogeneous problem, right? The same inhomogeneous problem, you can take their difference and produce a homogeneous solution. This would be interesting in a physical sense, like maybe you have two springs. We have a given spring, you put different forces on it, and you can discover the characteristic of the spring by studying the response of the spring to different forces, external forces. You discover like the spring constant and the mass. I'm being fuzzy here. This is not that problem, but that problem is also linear. I'll shut up. So guys, have a good weekend. I'm hopeful we have that recommended homework list to you sometime soon. I should have the project, the MATLAB project that Dr. Smith wrote up that we're going to all do, posted for you sometime soon. He said that you guys can already do the first part of it because it's basically just coding the Gauss-Jordan elimination. So you should be able to do that part. But then the part on matrix multiplication, we're still kind of getting to. So anyway, stay tuned.
Quiz on Tuesday.
Oh yes, quiz on Tuesday. Good point.
So,
Short quiz.
So if I don't have the textbook yet, how can I study?
You should get a textbook.
I order it.